Let's take a look at lesson 3.4. 3.4. Now, what you might notice is number one, I have posted on my screen some properties of logarithms. Before we get going, when we expand, just to kind of give you an idea, when you expand, what I would recommend as like a pattern of how to look for it is to first go through the product property. Whoops, it's going right. Let's do this again. What's going on here? We'll try this one more time. The first, I don't know what's going on. To try to do either the product or the quotient. Secondly, do the power. And then third, if possible, simplify. And remember, you can simplify any logarithm that has no variables. If so, whenever you finish this out and expand it out, any logarithm that doesn't have a variable, you can simplify. I'm going to give you a few minutes to try this on your own. There are your three your three properties. See what you can come up with. All right, now as we look at number one, the thing I notice when I look at this is where I need to first establish, is it product or quotient? What did y'all decide? Is this a product or a quotient? Quotient. So one log dividing is equivalent to multiple logs subtracting. So the factors in the numerator become positive logarithms. So these factors, I see three factors in the numerator, will become positive logarithms. And my denominator, I see one factor, so it'll be one negative logarithm. Notice this is a 2 log, so all of these will have 2 log base 3s. So as I start writing this out, we would be equal to 2 log base 3. And I'm going to do the 9 first. And positive logarithms, or the numerators, add together, like the quotient, or like the product property. So then it'll be 2 log base of 3 of x plus 2 log base of 3 y squared. Finally, we get to the denominator. That will be a negative log. Negative 2 log base 3 of z cubed. That right there was the quotient property. So I'm going to put quotient property on the side. Quotient property. Okay, after you do the quotient property, what should we try next? The power property. Do we have any powers? What can I do with the power? Move it to the front. Now it becomes like a coefficient. Now coefficients multiply. I want you to know that. They multiply. So the reason I put 2 log on the bell ringer is just to make sure you understand what happens when you move these to the coefficients. Will these 2 and this 2 add together? No, they will multiply. This 3 and this 2 will multiply. So this would be equal to 2 log base 3 of 9 plus 2 log base 3 of x. Those 2 don't change, but here we go. This is 2 times 2. What's 2 times 2? 4 log base 3 of y. And then finally minus 3 times 2 is 6 log base 3 of z. Finally, to finish off the problem, let me write down here, that is the power property. You would try to simplify. 2 log base 3 of 9 can simplify. Any logarithm that's just numbers, no variable, you can simplify. You could type this in the calculator, or you could ask yourself, the way you translate a log, 3 to what power equals 9? 3 squared equals 9. So the answer to this logarithm is going to be 2, and then you multiply it by this 2. So what's 2 times 2? 4. Now we'll check that in the calculator just to make sure. Let me do that now. I'm going to just open up a blank calculator. So we're guessing 2 log. I'm going to do shift minus to get the base of 3. Base 3 of 9 equals 4. So we did do that correctly. And then continuing on over here, we have 2 log base 3 of x plus 4 log base 3 of y. And finally, minus 6 log base 3 of z. That would be my solution right there after simplifying. So that's what I did right in that last step. I just simplified. So there's number 1. Now, what about number 2? I keep reviewing this. It's from lesson 2.5. It says Brian and some friends go to the fair. Tickets cost the group $120, but Brian doesn't have a ticket to buy the ticket. It doesn't have to buy a ticket, sorry, since he has his DISD ticket. They spend $225 on games, divided equally among him and his friends. They all spent $40. How many friends went to the fair with Brian? What is it we're looking for here?
Friends.
Friends. How many friends? That means X refers to friends. All right, and how will we set up this type of problem like this? What's the like general formula going to look like? Okay, in theory, what's the theory of it? Average. If you're going to find an average, how do you find an average? The total or the sum divided by the number or whatever it is. So if it's people, if it's tests, your total score divided by the number of tests, you get your average score, something like that. Yeah, this is the theory. So here, let's go through and evaluate the money. I see $120. $120, is that that's tickets? Is it ticket $120 per person?
No.
Or is that the total for the tickets? Total. So if it's a total, that needs to be divided by some number of people, which we will establish later. They spend $225 on games. Is that a total or that's a total? So again, they didn't each spend $225, so that'll be divided by some amount. Here it says if they all spent 40. What is that telling you? That's the average. So I'll put it over here on the left. 40 is going to equal 120 divided by something. And this will be a plus 225 divided by something. All right. Who pays for the tickets?
Everyone except for Brian.
Brian does not pay for tickets. So is that X minus 1? Just X. Just friends pay for the tickets. So Brian doesn't pay for a ticket. Okay, what about games? It's divided equally. So it's not just friends, but friends and Brian. So 1 is equal to Brian. Now, this is just an insolve. If you want to do it that way, if you want to multiply by the denominators, you could. I'm going to use my insolve calculator. So go here, insolve. The way the insolve calculator works is it says first, type the entire equation in the line shown as red. So this equation right here goes on this red line right there. So 40 equals 120 divided by X plus 225 divided by X plus 1. Secondly, it says graph Y equals the left side of the equation. Now, what is my left side of the equation? I'm going to pause. What's the left side of the equation?
At this time, the teachers.
So Y equals the left side of the equation. What did we say the left side of the equation was before the announcement? Look at the problem. What's your left side of the equation? What divides the equation? What symbol always divides it? The equal sign divides it. What's on the left of the equal sign? 40. So you need to have Y equals 40 here. Y equals 40 there. And then it says, secondly, or part of that, Y equals the right side of the equation. And it clarifies that's the right side of the equal sign. So you would copy this. I'm going to copy it by holding down Shift and hitting C. Hold down Shift, press C, that copies. And I'm going to go here, hold down Shift, press V. The intersection is the solutions. I will let you click to find out how many that is. I'm not going to just give it away. So you now can do so. So the solutions are always the X values. So after you click that intersection, it'll be that value. It will not be the negative intersection, just as a reminder. You can't have negative friends. So it'd only be the positive answer. You would need to click that. All right, I'm going to continue on now. And we're going to look at lesson 3.4, which is how to solve exponential logarithmic functions. Now, what's kind of weird about teaching this is that we had to break the lesson somehow, or the textbook makers, McGraw-Hill, had to break apart the lesson somehow. But truthfully, I've shown you all of this already because it's impossible to do the previous lessons without knowing how to solve a little bit. But this is first walking through the one-to-one property. You've heard me say it. That's just when if you have common bases, you could cross out your bases and just say the power is equal to other power, or the same thing with logs. If you have logs, you can do the same. So we're going to work through that today. So here's a way of solving these problems. Number one, if you have to solve for X anytime, could you go and use insolve?
Yeah.
Yes, absolutely. You could insolve if you wanted to. My guess is you don't want to just insolve all day. So I will show you the math of how it works. You're okay with that?
Yeah.
So what you want to do is have a common base. If you want to solve exponentials, these are exponentials. You need a common base. Do I have a common base? No. How I can get a common base is changing 16 to a base of 4, though. So I'll come over to the side using upside down division. How many times can 4 go into 16? 4 times. And I'm just going to stop there because I have a base of 4. So here, 16 is the same thing as 4 squared. So you could rewrite this problem, say 4 to the power of x plus 2 is equal to 4 squared. I'm going to put this in parentheses. So it's a substitution. Remember, substitute, the 16 comes out, 4 squared replaces it. So 16 is out, 4 squared replaces it to the power of x minus 3. From algebra, your rule with exponents when it's power raised to another power is you just multiply or distribute there. So this could simplify to become 4x, the power of x plus 2 equals 4, and you need to distribute that 2. So 2x minus 6. Okay, this is the one-to-one property. The one-to-one property says if you have common bases, you can remove the bases. So that is the one-to-one property that I just did right there. The one-to-one property says if you have common bases, you can scratch those out and say that x plus 2 is going to equal 2x minus 6. And now we just do our algebra. I'm going to, if you have a power, or if you're solving for x and your power is less than, or if your power is just 1, let me say it that way. Let me say it all over again. If you're solving for x and your power is 1, you can just get x by itself and it'll be isolated and solve that way. You don't have to factor anything special. So here, what I'm going to do is I will subtract this x across, and I'm going to add this 6. So what I'm doing is I'm isolating the x's and the numbers away from each other. So that's going to simplify out. The negative 6 plus 6 is going to simplify out. What's 2 plus 6? And then 2x minus 1x is x. We got our solution. X is equal to 8. Like I said, you could just graph this and use insolve all the way through. 4 to the power of x plus 2. Now watch this carefully. Hey guys, watch this carefully. When I go power and I put x plus 2, did that type in correctly? No. What's wrong with that? Didn't stay as an exponent. What you need to do if you have a group for the exponents on Desmos is you'll have to use a parentheses. So 4 to the power of x plus 2 equals 16 to the power of, and again, as a group, so I'm going to do parentheses x minus 3. And like I said before, you copy the left side of the equal sign and you graph that as y equals the left side. And you also are going to copy the right side and graph y equals the right side. The solution will be where the 3 graphs intersect, which we said the answer is 8. And man, you might have to zoom out for a mile to get to 8, the intersection, but I'm looking and I don't even see the dot. Well, the answer is 8. The red line represents where they're going to intersect because that's a vertical line. These are going over to it. I have no idea where these are actually going to cross each other, but they will finally at 8. Somewhere they will intersect at 8. That problem wouldn't be very good for insolve, but trust me, that's not the answer. They will intersect at 8. Okay, let's try part B here. Remind me first off, we did this property on lesson 3.2 and on 3.3. What can you do when you have a like a 1/3 as a base? If you wanted to treat the base as a positive 3 instead of a 1/3, what can I do? A negative power. So the first thing I'm going to do here is say that is 3 to the power of negative n. And that will equal, and I'm going to do the same thing over here. Now, if you do a negative power, that just changes one value. So the 1/3 became a negative n. If I want to do the same over here, I could rewrite this as 81 to the power of negative 2/3. Do I have a common base? Is this 1-to-1 right now? No. So let's reduce 81. 81, or factor it, rather, I should say. How many times does the base of 3 go into 81? 3 goes into 8. Very quick math there. 3 goes into 8 twice with a remainder of how much?
2.
With a remainder of 2, so I'll put the 2 there. 3 goes into 21 how many times? 7. There you go. 3 goes into 27 9 times. 3 goes into 9 3 times. I can stop there because it's all 3s. So 81 is equal to 3 to the 4th power. I'm going to erase that little 2 so we're not confused. That was just for division purposes. So 81 is 3 to the 4th. So here we go. 3 to the power of negative n is going to equal 3 to the power of 4 raised to the power of negative 2/3. So I just told you on part A. Now you repeat back to me. What do you do when you have a power raised to another power? You multiply them. So I would have 3 to the negative n equals 3 to the, when you multiply the fraction, the numerators multiply, denominators multiply. It'll be -8/3. Very good. Do I have a common base? Yeah, common base. So I can do 1-to-1 property. 1-to-1 property of simplifying. Which leaves me that negative n equals -8 divided by 3. If that's negative n, what does positive n equal?
8/3.
That's right. When you divide all this by -1, all that happens is sign switches. So positive n would equal 8/3. I'm going to try this one just to see if this one graphs a little better. So that 4, I'm going to go 1/3 to the power of n. I'll just change it to an x though for insolve. 1/81. This might need to be in parentheses. I'm not really sure. Let me do this just in case. I'd hate to have a stupid error because I didn't put a parentheses here. So I put those in parentheses to the power of 2/3. 2/3. There you go. Copy the left. Copy the right. This intersection is easier to see. It says 2.667. And if we divide 2.667, if I hit this fraction, let's see what it says. That didn't really help me. I'm sure if I put in more x's like, or 6's like this. Nope, still won't. Well, let's try 8 divided by 3. What is 8 divided by 3? Same value that we got there. So we did do it correctly. All right. Your turn. You can go ahead and try this one. DOL number 1. Now let's move into logarithms. So a lot of this, again, you will have seen before, but now we're officially learning how to solve it. So it says here 2 times, that looks like IN. What is that actually? That's an L. So it's a natural log. A log of a base of E is what that is. Just to write a little note on the side, ln of x is equal to log with the base of E of x. It doesn't matter what the number is. That's just a true statement off on the side. Just kind of a little note there. Okay, so if we were going to solve this algebraically, I still would go through the normal algebra rules first. So for example, what's the 2 doing to the natural log, the ln? Multiplying. What's the opposite of multiplication? Division. So though that we did not do that portion last class, you would still do normal math. Logarithms doesn't change your order operations or any of the math stuff like in that regard. Once you simplify the logarithm and have it isolated, how do we solve a logarithm? This I did tell you in lesson 3.2. How do you solve a logarithm once it's isolated? What's its inverse or its opposite, if you will?
Oh, you do exponential.
Exponential. So you would ask yourself, what's the base? And this problem, what is my base? It's a base of E. They won't show you an E, but the base is E. So I'll just write a hidden note or a note here. Hidden base of E. Hidden base equals E. So they won't show it on a natural log. So the base is E. What's my power? 9. And that would equal X. Now there's the answer, not rounded. For Alex's sake, that's the exact answer. This says to round to the nearest hundredth. So right there, I'm going to mark that as the exact answer. If we want to know what's the answer rounded, I'm just going to type this in just to get a blank line. Just click on your graph and press enter, and it'll give you whatever you have up on your Desmos. Just press enter, and it'll give you a blank line. And type in E on the keyboard, just E. power 9. E shift 6 gives you power 9. And we need to round this to the nearest hundredth. So that 100 has two zeros, so we need 2 decimal places. So 8,103.0. Would I say, does this 8 stay as an 8 or does it become a 9?
Oh, it stays at 8.
Stays an 8. And one thing I did wrong is if I want to be mathematically correct, I should do a little squiggly there because I'm rounding. If I want to be perfect, do a squiggly like that. That just means you approximated the number. All right, that's the first one. Now this says using the one-to-one property. I wouldn't call that one-to-one property. Example 2b. I'll show you a one-to-one later. Here's 2b. So again, we're going to use our normal algebra steps. Notice that's a big 10. That's not a base. That's a big 10 there. All right, if you want to solve this, I would go through the normal algebra rules first, meaning when we solve, we do the opposite of PEMDAS. When you solve or try to isolate a variable, you do the opposite of PEMDAS. So you ask yourself, if there's anything I can subtract first. We can subtract 7. Do y'all think that's accurate?
Yeah.
I agree with that. So we'll subtract 7. And so now we have -3 log 10x equals 6. Now what?
Can you add by 3?
Can I add 3?
No.
What's the -3 doing to the log? It's multiplying. What's the opposite of multiplication? Division. So if you're ever stumped on that, just ask yourself, what is that number doing right now? Is it adding, multiplying, subtracting, dividing? And then you just do the opposite of that, what you see. So these will simplify the -3s. So I'm now left with log of 10x equals -2. So I have isolated the logarithm. Once you isolate the logarithm, how do we solve a logarithm?
Log 10.
You take its inverse, which is exponential. This has a hidden base as well. However, this time the hidden base is not e. What's the hidden base when you actually see the word log? 10. Hidden base is 10. So what I have here is 10 to the power of -2 equals 10x. So this had a hidden base. There's not a base shown. The base is 10. There's a hidden base here. So it's 10. That's my power. Let me remind you, I should have put it on this problem as a reminder. So I'm going to go back to the previous slide and put it on there. Reminder of how these work together. A base raised to some power equals a number. That's the exponential form. And in logarithm, a log base number equals power. These two were inverses of one another. And that's how I'm converting back and forth. These are inverses of one another. This is exponential. This is a logarithm. So let me see if I can copy this and just paste it again on the next problem. If it'll fit. That's not what I wanted to do. Let's try this again. There we go. This barely fits. I can make it fit more. If you're running out of space, just highlight everything and slide it over. Okay, so here's what I did. I took the base, which was 10. I raised it to the power, which was a -2, and that's equal to the number from right there. That's how I converted it from a logarithm to exponential. All right, to solve this, how will you get x isolated? If that's multiplying. What's the opposite of multiplication? Divide. So really what we have here is 10 to the power of -2 divided by 10, which is going to be 1/1000. That's the exact answer. That's the exact answer. How do I know that? Let me type it in the calculator to prove to you. 10 to the power of -2, and we want to divide that by 10. And if you press the fraction button on the left, it changed it to 1/1000. But as a decimal, it says round to the nearest thousand. 1,000 has 3 zeros, so 1,000 allows for 3 decimals. This one is exact. I don't have to round, so I don't have to do a squiggly. I'm just going to say x equals 0.001. There's my answer. That is an exact answer as well. So since both of these are exact answers, I guess I don't need that word exact answer. That implies one is and one's not. But that would be your answer. All right. Let's try one more of these. This time we get to apply some log properties. So something you could do here, there's multiple ways of solving this problem, but I'm going to use a log property here. What can you tell me about this power of 4? What can I do with the power of a logarithm?
Oh, you can do that power thingy?
I can use a power property and move that to the front. So this would be equal to 4 log 5 of x equals 20. That right there was called the power property. That's what that was. I moved the power to the front. Okay, how would you solve from here? And remind you, that 4 is multiplying. We would divide both sides by 4. And so we have log 5 of x equals 5. And now I've got this log isolated. Once you isolate your log, how do you solve a log isolated? Inverse. You take it to its inverse. So the inverse would be, what's my base? 5. What's the power? 5 equals x. It says round to the nearest hundredth. This won't round. Let's just see, what is 5 to the 5th power? This will not need a decimal. 3,125. Okay, before you circle that up, leave some space there. This is a little tricky. When I use my calculator, it won't totally agree. It'll agree, but it won't totally agree. What do I mean? Let me graph this and let me show you. This is press log, shift minus, base 5. And then in the logarithm, we have x to the 4th power. I'm not sure if you need that parenthesis or not, but I'll take it away. Okay, that's all going to equal 20. Copy the left side and paste it. Y equals the left side. Copy the right side, paste it. Right side. When I zoom out here, looking for my answer, it should have an intersection of all 3 graphs, red, purple, green. As I zoom out, how many answers do you see? 2. It has plus and minus. So here's what's weird, is this one technically is plus or minus. And if you're wondering why is there 2, but mathematically it's because of this power of 4. Since this had the power here, both answers are technically correct. What's tricky though, is once I move that 4, that power of 4, I could no longer mathematically have the negative answer. I want to explain why. There's a domain rule with logarithms. What are you not allowed to take with a logarithm? A negative logarithm. If the power of 4 is there, you're good because you can't have a negative. Even if x is a negative number, when you raise it to the 4th power, that means you have a negative times a negative times a negative times a negative. 4 negatives make a positive. So the negative answer would be included here because of the power. However, if they had started the problem with the 4 in the front, we would not include the negative. So it's kind of a weird problem. So it's plus or minus because the original power of 4 keeps, I'm going to say x to the 4th positive. Probably shouldn't have put that in parentheses since it didn't start there, just so you understand where I'm getting at. The original power 4 keeps x to the power 4th positive. So actually, that's why you have both answers there. And I'll put the in-solve picture right there as well. All right,
And she goes first.
of course. All right, DOL number 2. Go ahead and solve DOL number 2 here. Solve DOL number 2. Example 3. So now we get the true one-to-one property for logarithms, and it's the same idea as before. If you have a log base equal to the same log base and then everything else is isolated, you can simplify out those log bases. So on this particular problem, example 3a here, I have 3 logarithms. Now let me tell you what's not one-to-one. What's not one-to-one is just look at this and say, oh look, they're all log base 2s. Let's just simplify, simplify, simplify. That's not one-to-one. Because how many logs did I just cancel out there? 3. That's not one-to-one, that's 1-to-2. And we don't have a property for that. So what you would have to do first is simplify a couple of logarithms. So we know a rule. These two are subtracting. What's the rule about 2 logs subtracting? They're actually dividing. So what I could say is this is like log base 2 of 5 equals log base 2, and just make it division. The positive log goes to the numerator. The negative log goes to the denominator. That right there we call the quotient property. And now I'll ask the question, how many logs do you see? 2. Both sides, they're isolated. So now we could do the one-to-one property. Say 5 equals 10 divided by x minus 4. There is the one-to-one property. If you wanted to solve this by hand, which I'm doing, obviously we would, if we're going to use a calculator, we've done it on step 1. But if you want to solve this by hand, you multiply the x minus 4 on both sides. You multiply your denominator out of there. So now I will distribute. What's 5 times x? Or x times 5? 5x. And what's negative 4 times 5? Negative 20. All that equals 10. We're working through our algebra 1 here. We're trying to isolate this x. How do I get rid of this minus 20? We add 20. And so 5x equals 30. And now we're about to get our answer. What's that 5 doing to the x? Multiplying. The opposite of multiplication is division. Let's divide by 5. And we come up with our solution that x equals 6. All right. Now, some students might have pointed out, well, couldn't you have just typed this in the calculator from the start? Yes, we could have. We could have just in-solved right from here. Whoops. Keys are not, my hands are not in the right place. Here we go. Log base 2 of 10 minus log base 2 of x minus 4. You'd first type that in. You'd copy the left side of the equation, paste it. Copy the right side of the equation, right of the equal sign, paste it. And you would look for the intersection of the 3, which is at 6. So we did do that correctly. All right, part B. What can you tell me about this problem? Is this one-to-one?
Yes.
Are both logs isolated?
Yes.
You bet. If both logs are isolated, we can do one-to-one property right off the start. 1-to-1 property right at the get-go. So both those logs are gone. So x squared plus x equals 20. Now this is the first time we've seen this today. If you have a power greater than 1, remember this is now transitioning from what in Texas is algebra 1 to algebra 2. If your power is greater than 1 and you need to solve, you have to do so by factoring. That's just the math rule. So we do what's called the zero product property first. You need to set it equal to 0. So that's why I'm subtracting 20. Is when you factor and you want to factor to solve, you set it equal to 0. So I've now set it equal to 0. And you ask yourself, what's the best method of factoring? My personal favorite is GCF if possible, because it's the easiest. Do we have a common factor between these three items? No. My second favorite is X method for trinomials. Do I have a trinomial? Yeah, let's do X method. Remember X method, you have your A, B, and C, and you look for factors of A times C that add up to B. So in this case, I'll put M and N on the side. A times C, what is my A value if it doesn't show 1?
Just one.
1. So A times C is -20. My B is also a 1. So you're trying to think through, what are the factors of -20 that add up to 1? And a lot of you will already have this, but I'll write out my list. 1 and 20, 2 and 10. I like to do the multiples. So I'm finding the factors of positive 20 here. 1 and 20, 2 and 10, 4 and 5. I think that's all of them. Which one have a difference of 1? 4 and 5. How do I make it be a positive 1? 5 minus 4. Okay. From here, you would split your A power, which in this case, when I split that, it'll just be 1 power of X. So just be X plus 5 times X minus 4 equals 0. Finally, zero product property, like I was talking about before. If you had the zero product property, you set each one of your factors equal to 0, because the only way in math, not only math, in the whole world, the only way to multiply and get a product of 0 is that at least one of the factors has to equal 0. So you set each factor itself, X plus 5 equal to 0, and X minus 4 equal to 0. That is called the zero product property. You learn about that in Algebra 2. Very important property. Not that you have to know the name, but that's what it is. So what does X actually equal on this first?
-5.
-5.
And over here,
+4.
+4.
Okay. So you're good. So like you already knew. You bring your phone today?
Now, beware, whenever you have a negative answer with a logarithm, are you allowed to have negative logs? You check your answer to make sure that mathematically it still works. So this one does have a square, it might still work. Let's plug in the -5. What's -5 times -5?
Positive.
+25 minus or plus a -5. What's 25 minus 5? 20. So this one worked. But oftentimes, if you get a negative answer, it will not. Let's try 4. What's 4 squared? 16. 16 plus 4 is 20. So that one will also work. So in this case, both answers are good. But oftentimes, you will not have both answers. Now, something to make it really easy is if you just graph it, the calculator will always tell you the correct answer. It will not mess up. At least I have never found Desmos to mess up. So if I tried this one, you can see that there's going to be 2 answers at -5 and 4. Those are going to both be good answers. And I'll go ahead and just finish this off. So I copy the left side of the equation. I copy the right side of the equation. And sure enough, you will see that there are 2 good answers at -5 and 4. But you need to test those as you go on. All right. Your DOL number 3. All right, let's take a look at example 4. Now we're going to talk about how we can solve. And again, you've seen this before. If you need to solve exponentials, the way to do so once it's isolated, like this case, is to convert it to a logarithm. So earlier, let me see if it's really holding on one second. I made this chart. And so I'm going to pull that here. So on this particular case, we have the exponential form isolated. It's just a base raised to a power equals some number. So I can solve this by converting it to a log by saying log, then comes the base of 3, and your x and your 7 switch. So it'll be log base 3 of 7 equals x. Now that's going to be my exact answer. This says to round to the nearest hundredth. I'm going to go ahead and put here exact answer. Now there it is with no rounding, but this one I'm pretty sure is going to be crazy decimal. I'm just going to type this in, log shift minus base of 3 of 7, and we do get that value there. And so the rounded answer, or the approximate answer here, is that x is approximately, to the nearest hundredth means 2 decimal places, 1.77. On 4B, I look at it, and again, this is isolated. So I can say that I'll change it to a logarithm. So log, my base is e. These two switch of 8 equals 2x plus 1. Now there's a few things I can do to solve. I want to remind you, though, another reminder is that log base e of anything, so I'll just do x, is going to equal the natural log of x. So I'm going to first rewrite this as the natural log of 8 equals 2x plus 1. But to isolate the x, I would subtract 1. Now that's a natural log of 8, not just a normal 8, so I cannot subtract those two. So to make that clear, I'm going to do natural log with a parenthesis of 8. So you can see that those are not like terms. Minus 1 equals 2x. And then finally, that 2 is multiplying with x, so I will divide. And division works like multiplication. You need to distribute that through. So there's my exact answer. That right there is the exact answer. Let's type this in the calculator to get the rounded answer. The natural log, or let me actually just backspace this. The natural log of 8 minus 1, all this divided by 2, is that 0.5397 number right there. And so if we wanted to approximate this to the nearest hundredth, we'd say x is approximately 0. That 0.53 is going to round up to be 0.54, and that's the answer to the nearest hundredth right there. And again, if you wanted to solve this, I didn't even point that out on the first one, you could do so. E to the power of 2x plus 1. Oops, that didn't work. I need to do parentheses 2x plus 1 equals 8. And if I copy this left side and paste it, so we have y equals the left, and put an 8 there, the intersection of the 3 graphs will be my solution, which calculator kindly rounds to 0.54. With that, you have DOL number 4. All right, let's look at example 5 here. Now this time, notice I have bases that are not alike. And again, if you wanted to use insolve, go for it. You could insolve this. 3 to the power of, just put parentheses around this, 6x minus 3 equals 2 to the power of 4 minus 4x. And you would copy y equal, or the left side of the equation, left of the equal sign, and say y equals that, and copy the right side. Y equals the right side of the equation, y equals that. And you'll see there's my answer right there. Now, if you want to do this by hand, here's how we have to do this. It's a little trickier here. But what I'm going to do is convert this to a logarithm here. All right, so since I don't have a common base, what I'm going to do here is I'm going to convert this, since both of these are exponential and isolated, I'm going to convert this to a log. Now what's tricky is I got to pick one of these to be a base. I'm just going to pick 3 to be my base. And if I choose 3 to be my base, that 6x minus 3 is going to be, for this problem, my power. And I'm going to treat this over here as my number. And I'm going to do the inverse. And so when I take the inverse, I need to take a logarithm of the base. Base is 3. Now remember, your power and your number switch. So I will have 2 raised to the power of 4 minus 4x. all that will equal my power of 6x minus 3. So now I'm going to go through my log property. So I did an inverse there. That's what I did, is I went to the inverse of a logarithm. So I'll put in here a log inverse. I switched it to a logarithm. And so from here, I'm going to do my properties. I see I have a power. So I'm going to move this power to the front, a coefficient. And I need to put this in parentheses because it's got to multiply with this log. So I'm going to say 4 minus 4x times log base 3 of 2 will equal 6x minus 3. That's the power property. And now I could distribute and solve. Now this, we're going to have some crazy decimals in a moment. So this says round to the nearest hundredth. I'm going to go ahead and simplify out. When I multiply this, I would have, or distribute rather, I would have 4 log base 3 of 2 minus 4x log base 3 of 2. And that's going to equal 6x minus 3. Now, what I'm going to do here is I'm going to combine my like terms. I'm going to get the x's together and the numbers together. So I'm going to add 3. And over here, this doesn't look like a common term, but I'm going to type that in the calculator and actually get a decimal value there. Those two will combine. And I'm also going to add 4x log base 3 of 2, which doesn't look like a 6x, but these in the calculator will also be a decimal value. I can get a numerical value for log base 3 of 2. So when I combine these, what I'm going to have, let's see what this equals. 4 log base 3 of 2, and I'm adding the 3 right here. That's what I'm doing. Plus 3 is going to give me approximately 5.5237. I'm going to add a few more decimals there. 19. Okay, that's what that equals right there. And then over here, these two will simplify. And let's see what 6 plus, I'll add the x in a second, 4 log base 3 of 2 is approximately the decimal. 8.2, no, 52, I'm sorry. 523719. And this is with an x. So the last thing to do to solve this, since those are multiplying, is I would divide. So to isolate the x, you would divide 523,719, 8.523719. When I divide those, I should have my approximate answer, which we already had from Desmos over here the first time, 0.65 if I round it, 0.65, 0.65. And let's see if our mathematical values turn out to be the same. So I'm taking this number here. You know what? Here's the exact answer. I'll just take that, and I want to divide this by this answer. And you can see there's the exact answer, which does round to be 0.65. So that's how you would solve that mathematically. I'm gonna go ahead and add this over. And with that, you can try dual number 5. I would again recommend to you that you just use InSolve for this one. Now let's take a look at example 6. I want to remind you or let you know that whenever you're using exponentials or logarithms, you can use any algebra rules you've learned in the past. For example, this is set up as a quadratic. What do I mean by quadratic? This is a 3-term trinomial. And you could use X method to solve this. You could treat it as my A is however many e to the power of 2x's, which in this case is 1. My B would be -1, and my C is -2. And you could do an X method factoring just to solve this. So A times C is -2. My B is -1. We would try to solve two numbers that multiply to be -2 and add to be 1. The only factors of 2 are 1 and 2. So it's going to be 1 and 2, but how do I make it be a -1? It needs to be 1 minus 2. So what would you do? Like always, you next come up and you split the a term's power. So it'll be 1e, but instead of the power of 2x, it'd be the power of 1x. E to the 1x, as I split it, plus 1 times e to the 1x minus 2 equals 0. Since these are multiplying with the product of 0, this is the zero product property. We could say e to the x plus 1 equals 0, and e to the x minus 2 equals 0. That's the zero product property, meaning if you're going to multiply and get a product of 0, one of your two factors must be equal to 0. So we solve each one individually. I subtract 1. On the other answer, I'll add 2. So e to the x equals -1. Or here, e to the x equals +2. We're going to have to find out that this is not a legitimate answer. E to any power cannot be negative, but the way you would determine that is you would switch it to a logarithm, and you would say log base e to the of a -1 has to equal x, which is the same thing as natural log of -1 equals x, and this is not possible. You cannot have a negative logarithm, so that's undefined. So that answer is not going to be good. But over here, we do have a good answer. You would convert this to a log, so it'd be log base e of 2 equals x. That right there is your exact answer. Well, I guess there's a better way of writing it. The better way of writing it would be to say the natural log of 2 equals x. So let me switch over, put that as the exact answer there. We'll type in the calculator to see what that value is. I don't need these anymore. This value is ln of 2, which if I ran into the nearest hundredth, like most of the answers previously, I would say it's 0.69 is my answer this time. And you could, again, just like we've been doing, if you wanted to, you could end solve this. Copy the left. Copy the right, which is 0. Their intersection should be our solution, 0.693, which is what we had, 0.69. With that, you can try DOL number 6. I'll give you a hint. One of these answers is not even a good answer at all. One of them is not even possible. Be undefined. And don't mess up the formatting there. That is just natural log. All right, let's take a look now at example 7. So some problems you might run into when you're trying to solve logarithms. Remember, the 1-to-1 property is not a 2-to-1 property. So as I try to solve these through, make sure you apply all your rules that if you're going to use 1-to-1, you first need to combine your logarithms here. These two logarithms need to become 1. They have a shared base, a hidden base of 10. So this is technically log of, and I would multiply. So x times x minus 3, that's the product property, equals log of 28. That's the product property there. Product property. Since I have a common log on both sides, log with a base of 10 that's hidden, you could simplify there. This is 1-to-1 property. And when I simplify, I'm going to go ahead and distribute this through. So we'll have x squared minus 3x equals 28. That right there was the 1-to-1 property of canceling the common logs. Now I have a x with the power greater than 1. So to solve, you need a factor. I'm going to subtract the 28 over to set it equal to 0 in preparation for the 0 product property. This is a trinomial. So to solve a trinomial, I would set my a is 1, my b is -3, my c is -28, and we would end solve. So you're looking for two numbers. that could multiply to be 28 or negative 28 and add to be negative 3. So the factors are 1 and 28. 2 times 14. 3 doesn't go in, 4 does 7 times. 5 doesn't, 6 does, that's all of them. So here I need to come up with two numbers that could somehow give me a negative 3. It looks like it's going to be 7 and 4. I'm going to get 4 minus 7. 4 minus 7 gives me negative 3. It multiplies to be negative 28. So now I'd split my a term. So instead of being x squared, it becomes x to the first power plus 4 times x minus 7 equals 0. And according to the zero product property, x plus 4 has to equal 0. X minus 7 has to equal 0. One of those has to be true. The only way to multiply and get a product of 0 is that one of those two things have to be equal to 0. Oops, got that wrong. Zero product property. There we go. And so my answers here would be x equals negative 4 and x equals 7. But as I said earlier in the lesson, beware anytime you have an answer of a negative with logarithms, to make sure it's still a good answer, negative 4 would be undefined. Negative 4 is not possible because you would have an undefined answer here. That's so another name for this is extraneous. You could say it's extraneous because it's not possible to have a negative log. Not possible to have a negative log. And in this particular case, if you plugged in a negative 4 there, you would not get the right value. You'd have a negative as well as a negative here. Those would not be defined logs. Those would not be defined logs, they'd be undefined. So that answer is not going to be good. You can insolve this and the calculator will only give us one good answer. Log x plus log of x minus 3 will equal log 28. Copy the left. Copy the right side. This only gives us one good answer, and the answer is 7. So we did do that correctly. All right. And your DOL number 7. Again, you could check some answers, and some of them very likely will be undefined and not even good answer choices. All right, let's go through and check for extraneous solutions one more time here. All right, now let's take a look at example 8. So once again, if I'm going to try to solve and I see that I have multiple logarithms, what I would like to do is 1-to-1. The problem is this is not 1-to-1. I have this number 1 here that cannot combine with either log. So there's a little bit of a trick here. And here's the trick. If you can remember what 1 is in terms of logs, you could make this 1-to-1. Let me tell you what I mean. 1 is the same thing as log. This is a common log. The base is 10. So a common log with a base of 10 to the number 10. That means 10 to the first equals 10. So what I'm going to do is I'm going to substitute here, this 1, I'm going to substitute that with a log 10. As you can see, all I've done is I substituted the 1 for a log 10. And the reason I do that is now I can make this 1-to-1 after doing a product property. I have 2 logs, common base, they're adding. I'm going to rewrite that as 1 log, and we will multiply 10 times the 2x plus 3. Now that I have, that was product property. Let me write that right here. Product property. Now that I have this 1-to-1, we will simplify the logs out. And so 3x minus 4 is going to equal, and I'll distribute here, 20x plus 30. Here I will simplify. So I'm going to subtract Let's subtract 30. I started right 20. Let me fix this. Subtract 30 from both sides. And I'm also going to subtract this 3x across. So 3. And we find out that we have negative 34 equals 17x. And since that 17 is multiplying, all I would do is divide by 17 for my solution. Now here we run into an x with a negative value, a -2, which I've said throughout the lesson, be very careful. If your x is negative, you need to check to make sure it's still a good answer. If I plugged in -2, notice that is undefined. There's not a real answer because 3 times -2 is -6, minus 6 more is -10. So that is not a real answer. No real answer. No real solution. Let me put solution. No real solution to this problem. That x minus 2 would be extraneous. It's another word you can use, extraneous. So now I have one for you to try. All right, and now example 9. It says this table shows the number of cell phones a new store sold in March and August the same year. The number of phones sold per month is increasing at an exponential rate. Identify the continuous rate of growth. So it says this is an exponential rate. Identify the continuous, not just that's exponential, it's continuous rate of growth. And so it's wanting an exponential model. We'll write down both. So what I'm going to do is I'm going to call March month 0. It's our initial data. And we'll say March. So April will be 1, May 2, June 3, July's 4. August would be 5 months later. So I'm going to use these months. So I'm going to close this calculator. And I'm going to go to my regressions and models, calculator number 7, and type in my data. I have months 0 and 5, and 88 and 177. This says exponential. It also says continuous, which is a little tricky. So we'll go ahead and put both. If you want an exponential model, like it says here, you would typically think this equation. So y equals ab to the power of x, where the a, according to right here, is 88. And the b is 1.15, which would mean that the rate is actually 15%. So my equation would be y equals 88 times 1.15 to the power of x. Or if you wanted it as a continuous exponential, you would use this form here. Y equals e to the power of rx, whoops, rx. And on this one, our a would be still 88. And the continuous exponential rate would be approximately 0.14. And so it would be y equals 88 e to the 0.14 x. And since I'm rounding, I should do a squiggly here. That would be my equation approximately. There with the rounding. Okay, and now part B. It says use this model to predict the number of months it'll take for the store to sell 500 phones in 1 month. So we want to estimate when this will get to be 500. So I'm going to turn both of these on, and I want to estimate when it takes to sell 500. So 500, both of these graphs are basically one on top of the other. It would happen in month approximately 12.3. So it takes about 12 months. From March, which means it'll be roughly March or April of the next year. To get to 500. Now you have one. Here, let's take a look at the ACP question. Newton law of cooling models the temperature of an object in time using that function. And it describes all the different variables here. It says a cookie was taken from the oven and placed on a cooling rack with a surrounding air temperature of 20 degrees Celsius. Now, I skipped over a lot of stuff, but I want you to see this 20 degrees Celsius is the surrounding air temperature. So when you look it up, the capital T's are the temperatures. The T of T means temperature at some time. This is the temperature, and it says of the surrounding medium, surrounding keyword there, surrounding. So that's where the 20 is going to go. T0 is the initial. So what we need to do here is put 20 there and 20 here. It says after 5 minutes. What's that telling us? Time. Time's the little t. So little t5. So t time, that's going to be temperature at 5 minutes. And this t is a 5. The cookie cooled to 48 degrees. So that 48 degrees, what temperature is that? Looking back at, is it the temperature at 5 minutes, or is it the original temperature, this 48? After 5 minutes. So would it be the original or the temperature at 5 minutes? Okay, so now I'm just going to erase that and put 48 degrees because that is the temperature at 5 minutes. So that goes there. If K is 0.35, let's put that in right there. That K is 0.35. What is T0? I'm looking, I have a variable T0 and I also have a variable E. How do I solve it if I have two variables? E is not a variable. E is a constant, isn't it? So you could just solve this to get your solution. So 48 equals 20 plus, I'm just going to do an X minus 20 e to the power of, I'll do a parenthesis here. There's a negative, don't miss the negative. 0.35 times 5. And when I copy the left and copy the right, I should get my answer. And once you zoom out like I have, you'll see the intersection right there for your solution. But I will let you do that on your own to find out what is the answer to this ACP question. And finally, the last one here says Jose is purchasing a new car for $27,500. He's purchasing a new car for $27,500. If the value of the car decreases at a rate of 11% per year, approximately how many years will it take for the value of the car to reach $12,000? What I'm going to do here is I don't need INSOLVE, but what I do need is my calculator for compounding interest, which is calculator number 9. I'm going to open that one up. And from here, I'm going to write down each of the values. So my A is the final amount, which in this case, it did give me the A. We're purchasing a car for $27,500, but we want to know how long does it take for the value to decrease to $12,000. That's the final amount. The starting amount on this particular problem is $27,500. The rate, it says it's decreasing. So decreases means it's going to have a negative rate. And it's decreasing 11%, which is 11 divided by 100. The time is what we're looking for. We don't know how much time there's been. It says approximately how many years. So that's our X. And on this one, when you try to determine, is it N or E? Does it happen a certain number of times per year? Or does it happen exponentially, continually? You look for the word compounding. And this one doesn't even have compounding. So if it doesn't, odds are it's going to be one time per year. And that's exactly what this does say. It does say per year right here. It says one time, or it says just per year, which means once per year. So we're going to use the formula with the N, and N needs to equal 1. So as I plug these in, the A is going to be 12,000. The P is 2750, 2 zeros after. Again, no commas, no dollar signs. My rate needs to be negative 11 divided by 100. My time is X. N is 1. We are looking for the formula that is per year, not continuous or exponential, because it didn't say continuous or exponentially. So I'm not going to use the one with the E, so I'll turn that one off. Your answer is going to be the intersection right there for the years.